Alright, this is part 2 of the buffer screencast, and we've really just got one thing to finish up here, which is what this little blurb says, that if we're careful, we can use the Henderson-Hasselbalch equation when we're dealing with a weak-based system buffer, as long as we make sure what we're plugging in is a pKa and not a pKb. So in order to do that, you want to know about a special relationship between pKa and pKb, and that is going back to Kw. And if you remember, Kw is the equilibrium constant for the ionization of water, and that's equal to 1 times 10 to the negative 14th at normal conditions. And so most of these are going to be either run at 298 or 273 Kelvin. So the relationship is that Kw is actually equal to the product of Ka times Kb. So what that means is, since we've always know Kw, if we know Ka, then we can solve for Kb, and vice versa. If we know Kb, then we can solve for the Ka. If you keep in mind things like, ammonia is a base, so it has a Kb value. Well, when that thing undergoes hydrolysis, it's going to form NH4+. And so NH4+ is the conjugate acid. So it wouldn't make any sense to use a Kb for NH4+. You would want to use a Ka. And the way to get the Ka is to plug in ammonia's Kb times x, and then set it equal to the 1 times 10 to the negative 14th. So let me show you how that works. We've got a buffered system in this practice problem. Ammonia, that's our weak base. They give you the Kb value. If they didn't, you can always look it up in a table. And then again, they give you this salt, and so it's a soluble salt. It'll break up into NH4+ and Cl- when you put it into solution. So it wants you to calculate the pH of the solution. Of course, we could go through our ice table and solve it that way. But once you've seen the Henderson-Hasselbalch equation, usually students like it and want to use it. So when we write out this reaction, we see that this OH is being formed. So that's, we've got a Kb value for NH3 because he produces OH-. But the Henderson-Hasselbalch equation, as you guys saw, relates the pKa and the ratio of the conjugate base to the acid. So in order to use this equation, we would have to make sure we're plugging in a Ka. Alright, so the concentration of ammonia is 0.25 molar. The concentration of the NH4+, since this breaks up and it's 1 to 1, it'll just be equal to 0.40. We don't care about the chlorine. So this is equal to 0.40. Alright, so this is our acid, and this is our base. Okay, so to get a Ka for NH4+, we need to use the relationship that Kw equals Ka times Kb. So 1 times 10 to the negative 14th equals the thing we're looking for times 1.8 times 10 to the negative 5th. So when I solve for that Ka, I get 5.6 times 10 to the negative 10th. So now I'm going to use the Henderson-Hasselbalch equation. pH equals pKa plus the log base over acid. pH equals the negative log of the number we just got, 5.6 times 10 to the negative 10th, plus the log. Alright, make sure we get it right. So the base was the 0.25 molar, so he's going to go on top. And the acid, which is a conjugate acid, is the 0.40 molar. So this simplifies to pH equals 9.26 plus a negative 0.20. So our final answer is a pH of 9.06. And then you ask yourself, hopefully, before you move on, does that make sense? The buffered solution contained a weak base, so this pH better be greater than 7, which it is, and so that makes sense. If you had inadvertently plugged in the pKb here, you're going to get a pH that's less than 7. So if you stop and you just ask yourself, does that make any sense? The answer should be no. And so a lot of times you can catch your mistakes by doing that. All right, so that wraps up the introduction to buffers. What I wanted to do with the remaining time, I found this nice problem set online, and it's a nice mixture of problems, calculations, as well as concept questions. So I thought what we could do is go through these together. We can read the question, you can even pause the screencast, come up with your own answer, and then turn the screencast back on to hear the discussion. So the first one's pretty much an easy one. It says, what does a buffer do? So asking for just the general definition of what a buffer does. So our choices are keeps the pH of a solution constant. That's not too bad because buffers do resist changes to pH. Keeps the salt concentration of a solution constant. That's not necessarily true. And then the last two say keep the cation and the anion concentration constant. Neither of those are true, so our best answer would be A. And then question 8 asks, well, what substances are present in a buffer? So we talked on the last screencast that you've got to have either a weak acid or a weak base, and then in addition to that, you've got to have its salt. And so, by saying its salt, it's kind of generic, but you would also want to say that the salt contains the conjugate of the weak acid or the weak base. So we will go with A for that one as well. All right, number 9, the addition of hydrofluoric acid and blank, so HF, that really is NF, is a weak acid, so that meets one of the criteria. And then it says, and added to water will produce a buffer solution. Well, we've got the weak acid. The thing we're missing is the conjugate. And so we need a salt that contains F minus. So if I look at all my choices, the thing that contains F minus, correct answer would be C. All right. Number 10. Oops. All right. It says, which of the following could be added to a solution of sodium acetate to prepare a buffer? So we've got a salt, basically. It's supposed to be an H. You guys know how this goes with me. Sorry. All right, so there's our salt. Na can't hydrolyze because it came from NaOH, right, which is a strong base, so it has no affinity for picking up protons. But this acetate ion certainly can. And so we've got one of the components, we've got a salt. So we would want to find the acid that goes along with this conjugate base. So acetic acid is going to be our top choice. So when I go and I look, acetic acid is a choice. However, this one's a little tricky because it also mentions hydrochloric acid. And if you see that, you think, well, what in the world? Hydrochloric acid's a strong acid, so what would that have to do with buffers? But if you think about it, if we were to add H plus to this salt, right, CH3COO minus is present. And so when those guys get together, what are they going to make? They're going to make acetic acid. So by saying hydrochloric acid, that's a sneaky way of saying, look, we're going to take this salt, we're going to add some H plus, and you're actually going to make some acetic acid. So then you would have the two things you needed, acetic acid, which is your weak acid, and then the sodium acetate, which is your salt that contains the conjugate. Therefore, the best answer is going to be C, either of those. And I think this is the really tricky part, because you see that and you're like, strong acid isn't going to make a buffer. It actually will, because it can make the acetic acid. The other two are out, because they just don't make any sense. By adding ammonium acetate, you're just adding more acetate, which doesn't do anything. And then sodium chloride, neither of those guys hydrolyze. All right, number 11. Which of the following could not be added to a solution of sodium acetate, so again, the same salt, to prepare a buffer? So which of the following could not be added? All right, so again, this ammonium acetate pops up. By adding that, you're going to get some ammonium ions and some acetate ions, but that doesn't help you get the weak acid that we need. So definitely that one is out. Acetic acid, we just said, would form a buffer. Hydrochloric acid, we said, would form a buffer. And then nitric acid, it would also form a buffer because it's a strong acid. So again, it's going to convert the CH3COO to acetic acid, and then it would be present. So they're kind of trying to trick you, because a lot of kids would probably say, oh, the nitric and the hydrochloric and the ammonium acetate are out, and select E. But really, the only one that wouldn't form a buffer is adding that one. Number 12, which of the following could be added to a solution of potassium fluoride, so KF, to prepare a buffer? All right, again, K is out. It's not going to undergo hydrolysis, but F minus certainly can, because it comes from a weak acid. Excuse me. So we've got the conjugate base. What we need is the acid, right? So adding a base is not going to help. Adding potassium acetate, not going to help. Adding sodium fluoride, not going to help. Adding ammonium, not going to help. Again, a sneaky way to get your acid, they're going to add the HCl, which will interact with the F minus and actually make HF for you. So that would produce HF. So correct answer, C. Alright, 13. Which of the following pairs cannot be mixed together to form a buffer solution? Alright, here you're looking for things like, if they give you a strong acid and a strong base, like when those two things are mixed together, they're just going to be neutral. So that's usually an easy one. If that's not the obvious one, then you're going to have to look at the pairings that you have. So A is actually your classic buffer, weak base, and you got your conjugate acid there. For B, we've got sodium acetate, and they're mixing it with HCl. At first glance, you think, oh, that's not a buffer. But again, adding the strong acid, the H plus is going to get together with the acetate and form the acetic acid for you. So that would be a buffer. RBOH and HBr, strong base, strong acid, no way you're going to be a buffer. We'll look at the last two just for explanation. We've got a strong base and a weak acid. The weak acid's good, but we don't have a conjugate, so this will not form a buffer. And then we have H3PO4, which is a weak acid, and it's salt, and so that salt contains the conjugate base of the acid, so that one would be a buffer as well. So C is the only one that would not be. Alright, two more and then we'll wrap it up here. 14, which one of the following pairs cannot be mixed together to form a buffer? So same question, and again, this one pops out at me. I see KOH, which is a strong base, and HI, which is a strong acid. You mix those guys together, as long as they're in equal quantities, you're just going to get a pH of 7. It has no buffering capacity whatsoever. And if we look at these, we've got NH, so that's the conjugate acid. This is a base. We've got acetic acid. Again, it looks like, adding a strong base, what in the world is that going to do? But that's actually going to rip the proton off of this acid, form just acetate, right, by neutralizing it. And then you'll have your weak acid and your conjugate base. So that one would be a buffer. Same story with D, NH2CH3. By adding that HCl, he's going to accept the proton and form NH3CH3 plus, and then you'll have your conjugate present as well as your base. And then your last one, NaClO. ClO is our conjugate, so what we need is HClO, the weak acid, and what you're going to do is you're going to add HNO3, and that will actually form that acid. So all those guys are buffers with the exception of C. And last one, a solution containing which of the following will be a buffer? NaI and HI is out because that's a strong acid. This one is out, strong acid. This one is out, strong acid. D, CSF, and HF. This one will be a buffer. You've got a weak acid and its conjugate base.